Okay, welcome back, and now we're going to do an application type problem, and this has to deal with a decelerating car. Okay, so now it says a car traveling at a rate of 88 feet per second. So the rate of the car is 88 feet per second, okay, or 60 miles per hour. When the brakes are applied, the car begins decelerating at a constant rate of 15 feet per second squared. So that's the deceleration, right? So that's negative acceleration, right? So the acceleration would be negative 15 feet per second squared, okay? Right, because if this is positive, decelerating means it has to be going the opposite direction than the velocity. This is velocity, this is deceleration. If it was accelerating, it would be going in the same direction. Or have the same sign, right? In other words. Okay, now, it says how many seconds elapsed before the car stopped. So how long does it take the car to stop? Well, we need to figure this out. Okay? So, what can we do? Well, we can introduce some variables, right? So, a of t is equal to the acceleration, and then v of t is equal to the velocity over time, right? Okay? Or, a of t is going to represent acceleration. Okay? So again, the s of t, of course, is the position function, right? The distance. Okay? Now, so the position function is going to represent the position of the car beyond the point when the brakes are applied. Okay? So when the brakes are applied, that's going to be t equal to 0, and that's when the position function starts. Okay? So now, we know that the car is traveling at a rate of 88 feet per second. So the initial velocity is 88 feet per second, right? Okay, so let's write that down. So v naught, right? So, or v of 0 is equal to 88 feet per second. Okay? And since the car is decelerating, then we would write this as negative 15 feet per second, like I had. Okay? Now, the acceleration is the derivative of the velocity. Okay? So think about this. Okay? Acceleration is the derivative of velocity. So this is equal to v prime of t, right? So now we've got the derivative of velocity is equal to negative 15 feet per second. We've got the initial velocity is equal to 88 feet per second. Okay? Oops, hold on. Squared. So now, guess what? Now we have an initial value problem. Right? We've got a differential equation right? An unknown function relating to one or more derivatives, right? Unknown function involving one or more derivatives, and we have an initial value, initial condition. So now, what are we going to do? Well, we need to find the velocity function, right? So let's take the integral. So v of t equals the integral of v prime of t, right? Or let's do v prime. V prime of t dt, right? So what is this going to equal? This is going to equal negative 15t plus c. And now, since the initial velocity is 0, at t equals 0 is 88, well, guess what? When t is 0, we get c, so c has to be equal to the initial velocity. So guess what? v naught. $88. So we just found the velocity function. The velocity function is v of t equal to negative 15t, where negative 15 is the acceleration, plus the initial velocity, which is 88. Okay, now that we have the velocity function, guess what? If we want to find out how long it takes to stop, we got to find out when is the velocity 0. So now we just solve for time. So it's 0 equals negative 15t plus 88. Okay, this is a constant deceleration. So guess what? It's going to be t is equal to 88 over 15. Okay, and that's going to be seconds. Okay, and they don't ask for an approximation. So that's the exact answer. Now, the second question they have is how far does the car travel during this time? Okay, so we need to find the position function. So now how do we do that? Okay, so let's use the information that we have. Okay, so now we know that velocity is the derivative of the position function. So velocity v of t equals s prime of t. Okay? And so s of t is going to equal the integral of s prime of t dt, which is going to be equal to the integral of what? Negative 15t plus 88 dt. Okay, so now let's do this. So this is going to equal what? It's going to be what? Do it term by term, right? So this is going to be negative 15, right? And then we're going to what? Increase the power by 1 and divide by the power. So what we're going to get is we're going to get 15 negative 15 over 2 t squared plus 88t plus c. And so that is our position function. Now, we're not done, because guess what? We have an initial value. What's the initial value? What do we know about the initial position of the car when the brakes are applied? The initial position is 0, right? So we're given the initial condition that s of 0 at time t is equal to 0, right? Based on what we just discussed a moment ago. So here we have another initial value problem. Okay? So let's solve this. So if it's 0, then guess what? This goes to 0, this goes to 0, and guess what? C equals the initial position, which is 0. So that means s of t is equal to negative 15 over 2 t squared plus 88t. And now we plug in 88 over 15. And so now what we do is we want to find the position that the car, when it came to stop, how far did it move? So the s of 88 over 15 equals negative 15 over 2 times 88 over 15 squared plus 88 times 88 over 15, right? And so now, how do we simplify this? So we got this answer. So now the answer to this question here is we're going to simplify this. And what are we going to do? We're going to get, this is going to end up being 88 squared over 30. In fact, that's going to be negative. And then plus 88 squared over 15. Okay? Which means it's going to be 88 squared times 2 over 30, right? So if I simplify this, what do I get? I get 2 times 88 squared minus 88 squared, which gives me 88 squared over 30. Okay? And that is in feet. Okay? Now, do they give an approximation, or is that... And so it turns out to be approximately 258.133 feet. So this car going an initial speed of 60 miles per hour and then puts on the brakes with a deceleration of 15 feet per second squared will go 258 feet approximately before it comes to stop. Okay. That's a long distance. Okay, that's it. Have a great day.